Swayamprabha. Digital India. Educated India.
So far we have discussed about various conservation equations, and we have seen that how these equations can be derived, and subsequently we will see that how these equations can be used to address various problems related to microfluidics. So entering into the specific topics of microfluidics, we will first discuss about pressure driven microflows. Why we are interested about pressure driven microflows is because pressure driven microflows are interesting and important from many points of view. Like if you think of classical flows, that is fluid flows occurring over macroscopic scales, one of the most obvious ways by which you drive flow through a system, maybe a piping system, is by pumping. So that is a pressure driven flow. So in microfluidics, of course we do not use the same type of pump that we use in macro flows, but you can generate pressure gradients by various mechanisms in microflows to actuate the flow. While there are certain limitations, I should not say disadvantages, better to say limitations associated with this method, there are still some obvious advantages. So we will start with this in terms of flow actuation mechanisms in microscale flows. So just like for any topic, we are interested about first the motivation, right. Why are we interested to study pressure driven flows in microfluidic systems? So several such applications are there, like for example you can have pressure driven microflows in biophysical systems in general, and human body mechanics, in human body blood flow dynamics in particular. So how is it possible? As I discussed earlier, that in human body you have a hierarchical structure of the sizes of the blood vessels. So you have large arteries, large veins, small arteries, small veins, arterioles, venules, and microcapillaries. Microcapillaries are nothing but like human body microfluidic channels, microchannels in human bodies. Of course there are several complexities associated with those microfluidic channels as compared to engineering made channels or engineered channels. So we will not get into those details right now. We will discuss about those issues when we talk about fabrication of microfluidic channels, that what are the complications that come into the picture as you go from the paradigm of microfluidic channel from an engineering point of view to a biomimetic microfluidic channel, a microfluidic channel that mimics the blood vessels of human bodies, and how to fabricate those channels. These are still very open topics in research, in modern day research. But in all these systems you have pulsatile flow of blood. So that flow is driven by a pressure gradient. Then you can have various technologies in which you can achieve microfluidic mixing. So for example, like one of the possibilities is that you introduce two fluids by a driving pressure gradient and allow the fluids to mix by stretching and folding of the fluid elements as the fluid passes through an undulated passage or a corrugated passage. So that is one way in which you can achieve good mixing in a microfluidic system, where achieving mixing is otherwise a very difficult proposition because the Reynolds number is pretty low. We will see what is the consequence of Reynolds number in microfluidics, and the corresponding hydrodynamics in many cases is classically known as lower Reynolds number hydrodynamics. Flow focusing is another application where you can see that you can basically have a fluid in the core and two fluids injected from the sides, and this essentially creates a microfluidic stream. So that is called as flow focusing. So flow focusing is used in many applications, like flow focusing is commonly used for generating droplets for example. So that you can see in one of these slides. So starting from this physiology to engineering applications. So you can see the wide gamut of applications of pressure driven microfluidics, starting from the human body dynamics, understanding the mechanics of human bodies, to like engineering devices for practical applications like mixing, droplet generation and all. I mean pressure driven flow is inevitable, and many times this pressure gradient is generated by a device which is a so called pump, but in most of the cases a positive displacement pump rather than a rotodynamic pump, and these types of pumps are called as syringe pump or peristaltic pump. So for example, this is a pictorial view of a syringe pump. So this syringe pump, like the basic mechanism by which a pressure gradient, driving pressure gradient is generated in the same way in which an injection syringe operates. So that kind of technology is used. So we will not get into the technology of pressure gradient generation at this stage, because we will be having a separate lab demonstration. So the way in which we have planned for the lab demonstration for this online video course is that we will have recording of the lab experiments which are going on in our lab, and then we will demonstrate the videos with those recordings of the lab experiments. So as far as practicable, we will include some very basic experiments in microfluidics which we will supplement with the theoretical discussion that we are having, so that it makes a sort of a complete package for the beginners. Now we will get into some of the fundamentals related to laminar pressure driven flow. Now these fundamentals are important to study microfluidics. Not necessarily these fundamentals are the only sort of theoretical basis on which microflows are based, but the very important fact is that these fundamentals are common to classical fluid mechanics with which most of you are familiar. So we will start with that. So let us say, let us go to the board maybe and discuss about this. Let us say that you have a channel like this. Fluid enters the channel, and when it enters the channel, let us say that the fluid enters the channel with a uniform velocity profile, just for conceptual understanding. Now when it enters the channel, the fluid is subjected to a resistance. The resistance is offered by the walls of the channel. So when the walls of the channel provide some resistance, what happens to the flow? If you consider, we will consider one section here and try to draw how the axial component of velocity varies, and if we draw the vectors with the axial component of velocity, that is called as a velocity profile. Remember, many times it is an illusion that when we draw a velocity profile, it gives an impression that as if that is the only component. Not necessarily, there could be other components which are not as strong as the predominant axial component, and that is why we are presenting the axial component as a representative of the velocity field, but that is not the complete picture of the velocity field. Nevertheless, we are presenting the axial velocity component in a vector diagram. So, at the wall what happens to the flow velocity? At the wall there is 0 relative velocity between the fluid and the solid by virtue of no slip boundary condition. Now, this statement sometimes is considered as a very serious offense when we are studying microfluidics, because there have been many observations and many theoretical studies which have revealed that that may not be the scenario in microfluidic applications. So, we will start with this assumption, but we will study a chapter later on the issues of slip or no slip boundary condition at the wall, and there we will study it more carefully and more elaborately. For the time being, assume that the no slip boundary condition may be one of the possibilities, still in many microflows no slip boundary condition works. So, you cannot definitely say that the no slip boundary condition will work or will not work, depends on several other things. What are those things we will discuss in details later on. Now, the velocity here is 0, because the velocity at the wall is 0. Now, if you come to a section like this, a location like this, here the velocity is somewhat greater than 0, but not equal to this free stream velocity. Same thing if we assume that it is symmetrical, same thing is for the upper plate. In this way, a section will come, or rather it is better to say a location will come, because it is in the same section. A location will come, a transverse location, where the velocity comes to a maximum and it does not change beyond that maximum. Okay. So, then it remains as a maximum like this. So, if we draw a velocity profile, the velocity profile is something like this. Because of some issues with drawing by sketching by hand, it may appear to be asymmetric, but it is I mean assume that it is symmetric in both sides of the channel. Now, let us consider another section which is located here. So, what we will do is we will draw the velocity profiles at the corresponding locations. Let us call it section 1 and let us call it section 2. We will draw the velocity profiles at the corresponding locations at which we have drawn the velocity profile for section 1. What is the velocity profile? If you join the tip of the axial velocity vectors, this red colored line that you see, that is called the velocity profile. Now, you come to this section. Now, can you tell that at this location, whatever was the axial velocity at section 1, at section 2 will it be more or less? It has to be less, because now fluid has come in more intense contact with the solid boundary. So, it is more seriously decelerated, right. So, it will be less. That means it will take a greater distance from the wall to come to the maximum. let us say that distance is here. Similar things we draw on the other side. Draw some vectors and then draw the velocity profile. So, the velocity profile shows that there is a section over which the velocity profile is uniform, but beyond that there is a variation. So, we can demarcate the flow field into two parts, one portion where there is a velocity gradient. Why is there a velocity gradient? Because fluid in that region adhering to the wall feels the effect of the wall through viscosity, and there is an outer region which does not directly feel the effect of the wall. So, the inner region is called as the boundary layer and the outer region in this case is called as the core region. It is not free stream because it is still a bounded flow, but it is called as a core region. So, like if you now make a sketch of the demarcating boundary of the two regions. So, let us say that just for clarity maybe I will draw it by a thick line instead of a dotted line. So, this is okay. This is the demarcating line between the two layers, I mean two zones of fluid. This is the boundary layer region, this is the core region, and this line that demarcates these two regions is called as the edge of the boundary layer. Now, this region, in this region there is something which is quite interesting that takes place. First of all, what happens to the core region? Let us say that UC1 is the velocity in the core region at section 1, and let us say UC2 is the velocity in the core region at section 2. Okay. Now, the question is which one of these is more, UC1 or UC2? Now, to understand that, let us assume that the density is constant to simplify the situation. So, if the density is constant, that means to have the same mass flow rate through the two sections, the volume flow rate must be constant, right. Volume flow rate is given by what? Integral of the velocity profile through the cross section. So, integral of the velocity profile, when we say integral of the velocity profile over section 1 is same as integral of the velocity profile over section 2. So, in section 1 what happens? In section 1 if you see that there is a region in which the slowing down effect of the wall is felt, that region is say of thickness delta 1. In section 2 that region is of thickness delta 2. Which one is more? Delta 2 is more. So, but the integral is the same. So, because delta 2 is more, that span over which the fluid slowed down is more, that means in the core region the velocity should be higher at section 2 as compared to section 1 to compensate for that loss over this section where it is slowed down, right. So, because I am repeating the logic again, because the region over which the velocity is slowed down happens to be more for section 2, that needs to be compensated by higher velocity in the core region. Okay. So, that means our first conclusion is UC2 is greater than UC1. Okay. When UC2 is greater than UC1, what can we conclude about the pressure gradient? Okay. First of all, when UC2 is greater than UC1, that shows that in the region outside the boundary layer the fluid is accelerating, right. This is one of the most fundamental differences between an internal flow and an external flow. If you have flow over a single flat plate, then the free stream u infinity is a constant. Here the so called u infinity is replaced by uc, that uc is a function of x. Okay. So, uc is a function of x if x is the axial coordinate. Now, uc is a function of x, that means what? The fluid is accelerating, I mean uc is a function of x means it is either accelerating or decelerating, but because uc is increasing with x, that means it is accelerating. Assume steady flow. When it is accelerating, it cannot accelerate until and unless there is a net driving force. So, what is that which is making it to accelerate? That is nothing but a driving piezometric pressure gradient. So, a driving piezometric pressure gradient, or better to say a driving head. The head may be pressure related, the head may be kinetic energy related, the head may be potential energy related. If the kinetic energy head is same at the two sections, then it is basically the sum total of. So, if you think of the head, let us write. So, P by rho g okay. Of course, you have to remember that when we are talking about this head, all of you understand this, right. I am not going to that level of undergraduate fluid mechanics, but if you feel that we need to discuss,